Okay, our second video for lesson 2 starts at part D, and another interesting thing with dot products, it's another way of helping us find an angle between two arrows or two vectors. So our book mainly asks us just to be familiar with this equation right here, that if theta is the angle between two vectors, u and v, then this statement has to be true, that cosine of that angle, cosine of theta, the angle between the vectors, has to equal the dot product of the two vectors divided by, it's going to sound complicated, but divided by the product of the vector's magnitude. And then if I wanted to take this equation and solve for theta, it would just mean taking inverse cosine on both sides. So that's just kind of an interesting formula. I want to get into, hopefully somewhat briefly in the video here, why that's true. So I'm going to pull up Sketchpad and just have a little picture for you to look at. I'm going to drag a few things over so you can maybe see the labels a little better. There we go. So here are two vectors. You have to kind of imagine an arrow right up here and an arrow right up there so that we have the direction. Theta is the angle between them. And in our kind of intro to this unit, when we looked at section 1, we said we could easily take u, vector u, and put it onto the end of vector v. So that would go right there. And then we also looked at examples where we went, instead of adding u, we subtracted u. So that's what this represents. So from here, the kind of starting point all the way to this point could be represented as v minus u. Okay, so this is vector v minus u, gets me right to that point. And what I want you to think of doing is kind of taking this and sliding v minus u, sliding it, this end sliding it up to here, and this end sliding it up to there. Geometrically, it does seem to fit. We just took this black line right there and we moved it up there. Okay, and so I want us to focus on this triangle that we end up with. Okay, now we know a way to represent the three sides. These are all vector names, but their length is just the magnitude. So we just put those bars around v and around u and around v minus u, and we have a way of talking about the length of those sides. And then theta is in the middle. And we talked about law of cosines quite a while ago, but law of cosines would be a way of representing this. So law of cosines says take the side that is opposite the angle and you square it, and it has to equal the two other side lengths squared. So we have this idea being squared and this idea being squared, and then we subtract 2 times the side length of one times the side length of the other times cosine of the angle that we kind of started with. So cosine of theta right there. If you look very carefully, let me just add something here. This is basically a squared equals b squared plus c squared minus 2 times b times c times cosine of theta. Okay, that is law of cosines right there. Okay, we're just using the description or the notation of vectors. Okay, so I know it looks kind of complicated, but it's just stuff we've looked at before. Okay, so as we go through and we work with a few other things here, I could take this and rewrite it like so. Okay, the whole right side of the equation has not changed. The only thing that has changed is this piece right there. Okay, and that's just using one of the properties that was listed, I believe, in part C of our notes, whatever section was right above this. We can, instead of saying the magnitude of this idea squared, we can say take that vector times itself, even though it's kind of a complicated idea right now. Okay, and then if we kind of keep working with this, the next line would say, well, the whole right side stays exactly the same. I've just kind of foiled this idea. I said, let's go vector times vector first to get this, and then outside to get this, and then inside to get this, even though these two things are technically the same because one of our properties says it doesn't matter the order. Okay, and then the last part, a negative u times a negative u gets me u times u, or it's equivalent to u times u. Okay, so that's all we did there. Okay, now this is where, again, we're just using some properties. I already talked a little bit about how these two things are basically the same, so we have two of them. They were both negative, so I need to keep them negative. Let me change colors here real quick. we have a property that says something like this is really just the magnitude of that squared. It's kind of the opposite of what we did here, where we said the magnitude is being squared. So let's rewrite it that way. So just notice that we went in one direction for part of this, and now we're going in the other direction. Okay, and the same rule is being used right there. Okay, so just a lot of algebra. I know it's complicated. I'm not going to ask you to repeat this, but I do want you to just try and make sense of what's going on here. Even if you need to pause and go backwards and try to go step by step, try to figure out what changes are being made. Okay, I'm going to give myself just a little bit more room. So let's see. I believe if I move that off to the side, perfect. Next line. Okay, this one's an easy one. Okay, we have this idea on the left and on the right. They cancel each other out. This is on the left. That's on the right. They cancel out. So that what's left behind is just moved down to here. Okay. Now, pretty easy one. They have a -2 on the left side, -2 on the right side. So those two things are going to cancel out like so. And then if you go back and you look at the formula that we were trying to prove anyways, I want to say that cosine of theta is off by itself. So if I divide by the product of these two magnitudes, I get this, and that is the formula that we're trying to use. So all of that lengthy video there just to kind of explain where the formula comes from. So let's try to use that a second in our notes. Erase all of that. We'll go back to our notes. Okay, so find the angle between the vectors if one is 3, 2 and the other one is 1, 0. For this example, I kind of like to start with the picture. So let's see if we can do that. Okay, so one of our vectors is 1, 2, 3, 3, 2, so we're going right about to there. Okay, so that is vector u. Write that down if we want to. Okay, let me change colors here, and the other one was just 1, 0. That's vector v. Okay, and so there are several things we need to figure out in our formula here. I need to know the dot product of u and v. I need to know their individual magnitudes, and then I can just plug that into a formula. So I have that kind of figured out already. I think you should maybe take a little bit of time to figure out where this is coming from. But I know that u, well, that's a u there. I know that u dot v, the dot product of those two things, is going to end up being 3. Okay? I challenge you, if you're not sure where that's coming from, try and figure it out right now. And if you can't, ask a question in class. Okay, we need to know the magnitude of u. And that ends up being the square root of 13. And then we also need, what else do we need? We need the magnitude of v. And that just happens to be 1. Okay, so we need to know those three things as we kind of set up our work here. So now that I have those three things, just a matter of plugging stuff into my formula. You can use either one that we have there. I'll just use the more basic, the first one, probably the one you can find in your book. Cosine of theta is going to equal the dot product, which was 3, over the magnitude, the product of the magnitude, so square root of 13 times 1. Okay, and then to solve for theta, you would just need to take inverse cosine of whatever this different color again, whatever this whole thing is, take inverse cosine of that, and you would come up with theta equaling about 33.7 degrees. And I don't have a calculator with me right now, but I really should probably be a little bit more specific than 33.7. I probably should add another decimal or 2 to my answer, but this is going to be my final answer. This was just kind of circled to show you what I was talking about there. But I do want to go back to and point out in our picture that does seem to look valid. This is probably going to be about a 33-degree angle. It does seem to make sense. Okay, I'm going to erase this really quick. And the last thing I want to point out here, if I scroll down, we do have a term called orthogonal vectors. That just means perpendicular. And these vectors will be orthogonal. U and v are orthogonal if and only if that dot product of u and v is 0. We've talked about that in our picture in our first video in this lesson. We talked about visually we can see that. But what I'd like to do in class is try and take a little bit of time and discuss why, if we know that this is true, why that also makes sense in the formula we have up there. But that is for later on in class. I'm going to stop right here.